the reason why I was supposed to go in first, but the reason why I was late because I like coffee too much and I missed my bus. But this is actually a very good metaphor that brings it to conversation why obviously I will take responsibility because I lost it. I didn't manage my time properly. It's nothing to do with barista, even though, think about this. So you have a barista that meets you at the place where you take in your coffee. And every day it meets you and asking every day what kind of coffee you want. Like he doesn't have any memory of our previous conversations. So I need to go about the recipe, what kind of coffee I want. Thankfully, I'm a simple person. I just want to have a black coffee. They're asking about milk. I say, no, I want a black like my soul. So just go straight. But what if there would be different barista that will, Zoom is capturing my clicker. Yep, capturing my clicker. Okay, I'll be standing here. But what if there would be barista that has the notes, just in case if they forget about something, then you have some sort of persistent memory of the things, and they know, oh, okay, this is Victor, and for Victor, we do have a black coffee, black like his soul. This is how he loves it, and this is basically two most important slides of these presentations. Difference between stateless stream processing and stateful stream processing. With stateful stream processing, you need to have a little bit of memory, where the stateless stream processing doesn't require. It's easy, it's fun and games. Today, we're going to be focusing on the framework. I don't know how many of you are familiar with this, but I'll give you my personal spiel on this. I'll show you some Java, show you some SQL. Hopefully, you will be excited. So we're going to talk about Apache Flink. Anyone heard used Apache Flink? All right, fresh meat. Not everyone. Okay, my name is Victor. I come from Confluent. For those of you who don't know, who knows what Confluent do? Essentially, we do a lot of things with Kafka. Okay, how many of you heard about Kafka? Now, oh, sweet, yeah, and we also do a lot of things with Flink these days. I wrote a book about Kafka called Kafka in Action. I'm a Java champion, so that's why there will be Java. It will be a lot of rant. This presentation will be recorded. Slides of this presentation, examples, discount codes, whatever, will be available there. Second most important slide from this presentation. All right. Still not working. Okay. What is Apache Flink? So first of all, Apache Flink, it is a framework. It is something that you write code against. The framework that exists for certain reasons. First of all, it solves the problem of distributed processing, help you to write highly scalable data processing applications. Flink can deal with bounded streams and unbounded streams, meaning that it can be used for batch use cases, and also it can be used in streaming use cases, and API is largely unified. So you don't need to write two different codes if you need to process, say, batch versus processing streams. The way how it's done, everything is stream in Flink, but your batch is just a corner case of stream because this particular stream has some boundaries. It's bounded stream. With this, you can access to any type of streaming system. It can be Apache Kafka. Obviously, we're going to be talking about Apache Kafka, but it's not only system available. Anyone using Apache Pulsar? That's what I expected. It's a crickets. Anyone heard about Apache Pulsar? All right, few people heard. Apache Pulsar, it's another data streaming platform, has a lot of similarities with Kafka, but it has slightly more different architectural choices. Amazon Kinesis, anyone heard about Kinesis? Kinesis also, it's another example of the streaming system. You can have a connector that will be streaming TCP packets directly from socket. And also it can be solved and processed using Flink, as long as you have a connector that knows how to bring this data into Flink. So let's talk about a few features. Being as a framework, Flink can deal with multiple different data sources. And the cool story about this, like I think it's a very common situation when different frameworks, they need to come up with some sort of set of connectors to bring data in set of connectors to bring data out. So Flink has a very big library of connecting virtually everything. But again, on my humble opinion, the only one source you need here is Kafka. And if you want to connect any other source here, you can use Kafka connector that 100% covers your situation with how the data will end up in Kafka. Unless you, like me, not like me, but you kind of like prefer not to live in the world of streams. And with these connectors, there's API. You can write your own connectors. Like I said, you can take the, say, you have a TCP packets, you have some very sophisticated enterprise software that only works with your company. You can write the connector to bring this data into Flink. And when the data is processed, it can be displayed as a result on the console, but it's not very interesting. You need to land this result somewhere. Flink is a system that's not designed to like serve data, say, for your API. You usually dump it to some system, like maybe cache. You can use Flink to do kind of like update of the cache, and this cache would be served through your APIs. It can serve the data into systems like Apache Iceberg for analytical purposes, where you can connect some systems like Snowflake and other systems to build this like nice dashboards out of it. So it only focuses on processing data. And the way how the data is represented in Flink, if you ever, in the last 10 years, dealt with the systems that do any type of data processing, most likely you heard term called DAG, called Direct Acyclic Graph. This the way how the modern systems describe how data will be flow through the system, how data will be transformed. Flink is not an exception here. It has also concept of similar to DAG. And it's this like topology we're going to talk in a few more details. So first of all, as I promised, first exemplar here, it's the Java API. Flink started as a, it's not my favorite language. It started in Scala. It's written in Scala because, I don't know, it was like probably location-wise, it was closer. There was also another, what word you used, kind of Scala was used in the data science world a lot, and a lot of data scientists was thinking to use Scala for things. Same thing that people saying like Python used for AI, but everyone runs Java in production. Anyway, so the Java API, highly inspired by things what you see in any Java framework. You will see stuff in Java util streams. You will see stuff in some collection frameworks, and essentially that's what you will be dealing with. You need to get input data in some shape or form. In this particular case, it's a memory application. It will be dumping data into the into this environment as an input stream. Next thing is that we have this like phenomenal class. It's called tuple 2. Do you know how many tuples there? How many? No. It's a Spark. In Spark, you have a 23, right? In Flink, they have 27. So the Flink is more superior than Spark. Jokes aside, it's a very hard legacy of languages that have a tuple as a native type, but it needs to be somehow brought back to our mere mortals to Java world. Anyhow, so the tuple represents kind of like a, it's not a pair. It's kind of like a set, probably, of elements that will be representing kind of like your row. And as a matter of fact, there is actually data type called row, but tuple, it's most common, most optimized, and everyone recommends to use it unless you have more than 27 elements in this tuple. Next thing is that you're applying your famous any type of function. So mapping, it's the function that doesn't do anything super exciting. That's part of the stateless stream processing. You just do some sort of transformations with this the mapping thing. And what it will do, it will return me a different result that will include word and how many words in this word there. So we need to bring the results back somewhere here. In this particular case, I'm using this just to print the results. And we need to tell this execution environment to execute. Very important thing. In the very beginning, we start initializing this execution environment. Essentially, it's the way how you get information about where you're running. Flink is system that allows to execute your jobs inside the cluster. So you need to understand where you're running, what kind of node. Sometimes you need to figure out locality of this data. We'll talk about this in a second. So in here, we need to tell environment, hey, so that's our topology. Go execute this. The way how this would look like, we do have this graph where operator or this particular node will be representing our function. It can be map, filter, aggregate, or something like that. And the connection essentially will be the function chaining. So how data will flow from one operator to another. So you can read data in parallel if your source supports this. For example, in Kafka, there's a concept of consumer groups, and you can scale your reads based on the numbers of consumers at the consumer group and number of partition in the Kafka topic. So you can have a great parallelization of how you can read the data from Kafka. Next thing is that based on certain criteria, you want to have data collocated with another data. For example, you're performing join of two sources, and it would be great if data with the same keys or keys that you use for join somehow will be allocated to the same node. So the join would be efficient and perform as you expected. So in this case, this data needs to can be using certain APIs. Data can be collocated. That's example. I was looking, yeah. So essentially, based on certain criteria in this particular case, we have colors yellow and blue, and they will go and will be performed on the different nodes. And at the end, we want to dump it somewhere, preserving order if you want, and everything will go into particular node. Let's talk about SQL in a second. So let me show you a little quick. I think it is. So that's operator. For example, we need to do some sort of transformation. So flat map will take the sentence and turn it into words. As a matter of fact, I think this is an example of quintessential hello world application of data systems. Who knows? You can read from here. It's a word count. So like I thought that there would be data engineers who knows how to pass interview, because I guess on interviews they're asking how to do word count in Spark and Hadoop and other data systems. Two things that you need to know about. It's a slightly different algorithm because it allows you to think not in a sequential order, but you need to think about how distributed system will tackle this problem. So essentially, I'll have a set of text lines that will come in, and after that, we need to turn it into result that will include count of words from these sentences. The way how we can do this, we take the sentence, we tokenize it. In this particular case, we just separate sentence by spaces, and we'll get another stream. From one stream of sentences, we flat map it. Flat map, it's a Scala term. How you call it in Python when you need to do kind of like explode something? You have a list of something, and you get bigger list. Flat map. Anyway, so we call it flat map. In the SQL, they call it explosion. Some of the dialects that you can have the keyword called explode. So essentially, we have a sentence. We explode this into stream of words, and after that, we're grouping by we get a stream that will be word will be representing our key and value. We are taking value and turn it into key. And after that, we run sum. So for this particular case, we have Apache Flink streaming data processing, real-time, blah, blah, blah. So when you see Apache, you count 1. When you see Flink, you count 1. When you see streaming, you count 1. And at the point where you see another Apache, because you already know that the Apache was there, you do Apache 1, because you just seen this for the first time. But when you have another stream that will present this with the sum method at the end, based on the key, you will get the result sum of all values for particular key. Let me run this real quick. Lesson number 1. Yep. Let me do this a little bit bigger so you can see. Running this Gradle. Run lesson 1. So again, this is how this output would look like on the first side. So we saw this Apache, we have 1, Flink 1, streaming 1, and only when the second time we saw Apache, we get 2, Flink 3, because we saw Flink here. Where is it? Yep. So we have a Flink here, Flink here, Flink here. So in this case, output of this operation was another stream. So I don't want to go like very deep here into kind of like a very esoteric term about stream to table duality, how stream will represent the set of steps that you need to execute and your table will represent final state. But most important thing, so since we're in the bank and this money metaphor always works for people because people pay attention when someone talks about money. So stream of data represents your ledger, essentially set of individual transactions. And table will represent final total. At the end of the day, when you execute all transactions, you have bottom line. That's your table, that's your state on this given moment of time. If there would be a new record in your ledger, your bottom line would change, your state would change. So that's why here, my console, in this particular case, just read a result of the stream. So I didn't output this in anywhere. But at the end of the day, we will receive something like a key value in, say, some sort of like a cache system, key value system, where we can, by calling some of the record based on the Flink key, we'll get number 4. Does make sense? Of course it does. It's the basic of data engineering, right? Are they still asking this question at the interviews? No? I don't know. So next thing is that some people say like, screw this JVM, screw this Python. I know SQL. When I was starting like learning and learning all this like Java stuff, the WebSphere, I said, I'm not gonna learn SQL. Like, I don't need this. I have Hibernate, I have this object relational mapper system that will magically turn all this SQL stuff to my Java methods. I don't need the SQL. And 20 years after, we're still here, SQL 92 still going strong, and Flink provides this very interesting interface. So it gives you ability to use SQL as DSL for writing your jobs. So you can say that, okay, I don't want to deal with jars, dependencies, all this kind of stuff. You start Flink SQL CLI, you run this command, and you don't need to do anything. Flink will parse it and compile to the job, submit this job across the cluster, and you will be golden. And the way how the things would look like on this topology, this is the way how the Flink would look at your query and turn it into something that will be executed. So I always found incredibly frustrating in SQL that you need to read this from the middle somewhere. Like not from the top, but you need to know from. This is the first place where your data is coming from. So in this particular case, it comes from the table. In Flink, everything is a table with the different characteristics. If you want to have this kind of like a streaming abstraction, it's also table, but table that will be constantly giving new results. If you're dealing with Flink and using the kind of like a bounded abstraction, it still would be table and it still would be similar semantic how it does in regular SQL. Now, we're starting in the very beginning our journey. As you remember here, we started at the source. First one is going for the source. So in this case, our from will be represent the source where the data coming from. Next thing is that we need to specify what exactly we want to get this our projection. We're getting color and getting count. Now, here we're also performing a filtering, so some of the nodes will contain state, some of the nodes won't. So in this particular case, our count node will require some state. Why it is important? Because this count can be too big to recount or recalculate many times. So you need to preserve it in case of cluster failure, in case of restarts. You're running this in someone else's computer, aka cloud, and you don't know where your data is, so you need to make sure that somehow your processing will be survive and stateful and persistent. And another operation like filtering doesn't require state. So you just need, you have some sort of like predicate here, and based on this predicate, you just decide to pass this result to another node or not. So with this, Flink has data streaming API, something that is well known and very much loved by many developers and people. There is this SQL that data analysts love, or they claim they love, and there is something in between. So you can have both of this of two worlds. You can have still like Java API because you want to use your favorite libraries that needs to be brought up in your application somehow. Or you can use the deployment model that is already well established in your company. But writing too much, processing things, you still can leverage some of the SQL bits. So for that, there's the table API. And the good thing, table API is also available not only in Java, but also in Python. So there's a PyFlink project that allows you to write these jobs. It still will be Java at the end of the day, but it will give you a nice and fuzzy feeling that you're running your Python stuff there somewhere. JVM can run basically virtually any language. So it's superior platform, I would say. Yes, there's a misconception that SQL API from Flink uses data stream. It's two parallel APIs that use access to low-level runtime on the Flink side of things. But they are working slightly different. So with this SQL and table API, you can rely on some sort of optimizations. So there's a special process that can make your query a little bit more efficient than you wrote or you intended to write. And this is the optimizer part that is not available in data stream API. Data stream API is very, to the point. So let's take a look quickly. Works great with Kafka. So there is a connector that allows me to read the data from Kafka topic and also potentially eventually write data in Kafka topic. So, but in this particular case, I'll show you a very simple example of aggregation. So I have a Kafka producer that generates some of the these. Let me show you quickly. My Kafka is running obviously in Confluent Cloud because I don't want to lose my my data in case if I lose laptop or my laptop will die during the demos. So that's the order information. So order information flows into Kafka topic would look something like this. By the way, if you're using Kafka and you are not despised of Visual Studio Code, there's an incredible plugin called Confluent extension for Visual Studio Code. Gives you ability to look in Kafka topics, give you ability to see what kind of messages you have there, has ability to even kind of like see the schema of this data. If I will say the order value, it shows me the schema of this. So it's incredible. But data-wise, it's just totally made up. It's automatically generated, but it still has some structure. We can try to make something out of it. So in this particular case, I have SQL that will be running aggregation per customer, per category, and will tell the result, hey, there's customer 04 spend $137.83 on the books, and so far so on. So since it's the console, the output will be constantly changing, but if it would be result, it would be written somewhere in some database, you will see the result would be kind of like an upsort instead of putting more and more new results. With this, we also have ability to run some more serious stuff, say VIP detection. So in this particular case, I have this, if customer spends blah, blah, it will be regular, spends more, it's a VIP, and even more, it's a premium. So I will be able to do this type of things with my Flink jobs. But what I wanted to show you, there's a SQL that I can, let me close everything. Bring it here, yep. No, I despise Visual Studio Code, yeah. So this is the result that, this is the query that we can execute, and if we want to have this kind of like a persistent view that will be constantly updated, we can create this view that will be resulting from this. And in this particular case, let me see if I will be able to execute this. So let me see if I'm running correct cluster. Okay, so let's see if my Flink's still up and running. Flink, refresh. Refresh. Here we go. Here we go. Yep. Where's my Flink? Yeah, that's my statement. Okay, so let's see if I will be able to run this one more time. We're talking about customer spending summary. Submit statement. So in this case, I run this as a select, and this system that outputs this result support me to kind of do upsort. So you will see something that you usually see on the dashboard, something that will be constantly updating. If we're changing the category, this category will be updating. So for example, we have these customers, total spend, a little bit obscene, but hey, it's a random data generator. We need to have a better data quality there. But this result can be saved, and now this result, even cooler, I can create another table that will be represented as a kind of like a table that will be written some external storage, and this data would be transformed and pushed by Flink into another Kafka topic or another database, if you'd like. Another example of this, and every time when I use like this operator like con, average, sum, this is where I am actually running a stateful stream processing. So these functions will have its own storage. And for the last few minutes, I would like to talk a little bit about the overall architecture. It will come back because it goes to cloud, from the cloud, spend some time. So last but not least, this is a very important slide. The way how the Flink runs jobs. There is a key component called job manager that will be, your code will be shipped there. Your jar or your PyFlink script will be shipped to job manager. Job manager knows what is going on in the cluster. So it knows how to take your job and spread this across task managers. Task managers will be responsible for actually executing your job. So with the task manager, if your connectors, your different sources, your sinks, those would be running on the task manager. So for example, if you're trying to read from the file, make sure this file somehow available for the task manager to access. If it's a different system like Kafka, Kafka also needs to be available from this task manager place. So each and every piece of your topology will be executed in tasks, and the number of tasks would be defined by, I don't know, like how generous are you with your resources. You can be very kind of like keep everything in control and only have things like very limited and scale this on demand, or you might have like over provision. So all these things are supported. Flink has integration with Kubernetes. There is a operator for Flink in Kubernetes. We run Flink in Confluent Cloud as a managed service, so you don't need to think about this stuff as well. And yeah, so I talk about this, but when I mentioned count, I said that we're going to return to this. And this is how we're returning this. So the count will be stored in a special place. It's called, I forgot how it's called. It's called, so there's a snapshot, and there's a, I forgot. I do have, like, you have a snapshots, because there is a snapshots and something else. One snapshot that will be created automatically, another one that you can create whenever you're maintaining your Flink cluster. I will be wrapping up, and I also will be available for advanced interrogation. Stream processing with Flink, it's awesome, but also it's available for executing your batch jobs. It's totally fine if you start thinking of batches as like some special case of the streaming. It has ability to transparently creating the state that I mentioned that you need to know only because it's there. Usually you don't need to worry about this. You don't need to do anything except kind of like configuring where these snapshots will be stored. I didn't talk about this at all, but this talk will require its own, hour and a half talking about event time, processing time, watermarks, how to deal with the late events, how the Flink, the different semantics dealing with these type of situations in the real world, how Flink solves this. And obviously there's a whole category of the talks when we can talk about the snapshotting and how the state recovery. For example, this diagram is significantly changed for Flink 2.0, where there was introduced this kind of like a new approach for dealing with state, where you can now save your state in object storage, and it will be constantly available for every node. So there's plenty of things to talk about Flink. The best place to learn about this in the website called developer.confluent.io. There's tons of materials. There's tons of videos, tons of courses. Feel free to go there. For some reasons, see, it's my favorite website on the internet. It's just like appears immediately. Everything what you want to learn about Kafka, if everything what you want to learn about Flink, stream processing and all this stuff, developer.confluent.io. My name is Victor Gamov, and as always, have a nice day.